read it when I was giving a talk at the SCG that I'd follow Nigel Anstey. I don't know if any of you have ever seen Nigel Anstey. He would fill an auditorium. They sat on a stage in order to get a seat. The aisles are completely filled. And then the next speaker, for 15 minutes, people are still trying to get out of the room, okay? Well, it's almost like following Dan Ebram, too. I don't think I'll ever be able to keep up with his very subtle humor in that. So I'll try, though. Oh, there they are. Okay, near surface events, friend or foe. Okay. Now, I have to apologize up front because I'm not going to show any equations. So those of you that thought you're going to see dispersion curves and the way to invert them, you're not going to see that. So let's just take a simple example here, and we'll have a little quiz. What you see there are what they call shingles, right there. Now, how are those shingles? What are they? And are they lateral gaps in a refractor? How are they generated? Do you have to have a very different type of media, maybe a couple low velocities with higher velocities in between? Now I'm going to try to solve this because it's my objective to provide quantitative insight into how near surface events are generated. But I'm lazy. I'm so lazy that what I'm going to do, I'm going to take the easy way out. I'm going to generate a catalog of synthetics. And then I'm going to show you. Now the message that I'm trying to bring here today for those of you the students is please always start with the most simplest synthetic you can. Never try to get the answer at the very beginning. Because if you do that, you'll never get an answer. So I'm going to try to start with the very simple model that I can. And in this outline, you'll see how it goes. I'll use elastic synthetics. Rob said it has to be something with elastic, what we're trying to measure. I said, okay. Let's try to identify events on a simple synthetic, a simple shot record. And then, once we identify events, we're going to see those events have simple asymptotes. And those asymptotes actually carry information about the near surface. We'll look at those. Then we're going to try to look at varying the near surface thickness. And after we do that, the last thing is we'll vary the refractor thickness. And I think you'll be surprised what this does to the guided waves and also to the trap modes and others. So now here's your first quiz. I want you to start with the simplest reflection model that you can think of. And when we're starting to look at this, you notice that the upper half space that I have here is made up of the same near surface material. So you might think of water going to the moon. And that's going to be an acoustic type of a model. Well, it's very simple. You can see that you have an event called P1, P1. That just represents energy going down in the first layer and back up again. So that's not very hard. So let's change it a little bit and put air in the upper interface, the upper half space rather. Now that we have air up here, we have a series of events sitting in there. And once again, this is only the acoustic model. Now we'll go ahead and try to identify those, and I've connected with red lines and blue lines some of the events that you see. This is the second stage of a model. All we've done is added an upper interface. And by the way, making that first upper interface the same as your first material really simplifies it too. Now, if you look over here, I'll give you an idea of some of my notation I'm going to be using. This is a P wave going down and a P wave going up in the yellow material. This is two P waves, two travels, the first multiple. There's the next multiple and the next. So you have three multiples sitting up there with the first reflector. Now on the other side, you happen to have some head waves coming out that are located in blue. These are the refractions or head waves that travel along the interface of the refractor. When you see P1, P1, that means it's a multiple of P and then a refraction. And then the next one is two multiples going like that. Now, very simple. This is an acoustic case, and we find out it's not too difficult to go ahead and identify them. So let's go ahead and look at one more thing about this. We said that the shear wave is equal to 0. And there is a bigger amplitude sitting right here on either side. And there's something that I call precritical. And what that is, that's separate. Is there any pink in there? No. No pink. I guess I lost the pink. It separates the leaky modes versus the trap modes. And this little angle right here was an asymptote, and it is P1 squared over P2, and that represents the P wave velocity. And you'll notice that past here is all the trap modes, and the trap modes mean that you don't get any reduction because of the reflection coefficient. So in here, on this side, when you bounce up and down, you always get a reduction by the reflection coefficient. Over here, you don't. That's kind of important when we start looking at the guided waves. Okay, now we have to put the elastic in. By the way, just to remember, take a look at this one and look at the difference. Acoustic, elastic. Acoustic, elastic. Look at all the additional waves that we get. Now, I put an AGC on this just so we can see the extra events down here and we're able to identify them. Let's start identifying them. The first thing we're going to have is a Rayleigh wave coming across, and you'll notice it's not dispersive because it's 850 feet thick up here. So we've got a very thick, no dispersion yet, and we have a P wave direct arrival, and we can't have a shear wave. Actually, it comes just a little faster than the Rayleigh wave sitting in there. That's one of the three one of the asymptotes that we're going to talk about a little later on. Now, let's look at it again without anything on it. Let's put something on it. Let's identify them. What is on that simple record? We have P1, P1, P1. These are the multiples in the primary. Over here, as we saw for the acoustic, you have the refractions. Refractions when you have a multiple, and then two multiples in a refraction. Okay, that was the P1 set. The next set we're going to look at is going to be, there's an asymptote that we have sitting on here, coming down. It's kind of an important type of an asymptote because at infinity, all these multiples are going to tie that asymptote sitting in there. And as the bed gets thinner, you're going to see them quickly approach that asymptote. Now we'll look at the converted waves. I had to do something for Dr. Rob, and here's the converted waves, and there they are. Now in the converted waves, lo and behold, it's P1, S1, but what about the other converted waves? They're all a function of the multiple of the primary waves going up and down sitting in here. Over here, once again, you'll see you have a P1, P2, and then S1. So that's a converted type of refractions sitting in here. And then finally, this is one here that we normally don't think about. This happens to be shear waves, and notice that's a P wave source. But as soon as that hits the surface, you got shear waves now coming down, acting like a source. And the one that really bothers us is this dude right here. See the S1, it comes down and it becomes asymptotic to the shear wave velocity sitting right in there. Then you have the multiple shears, they're asymptotic also to that S1. It's all the way down. So you got a lot of energy that's asymptotic to that first shear wave. So to summarize, what did we find for this very simple model? There are 24 different events that we identified in there, and they're broken up into P1 multiple reflections, converted reflections, or shear. And then, of course, we have a few asymptotes that we put in there also. So let's define some asymptotes now. Here are some asymptotes that we talked about. You're going to see there's a cone that's going to be identified by the P1 velocity in the first material. There's the Rayleigh wave that you can be identified. Now, if you get long enough wavelengths, maybe you reach this refractor down here, and that's going to have a Rayleigh wave. Now, there's the precritical. That's where you have trap modes on one side. These asymptotes, we're going to basically not move back and forth. And then there are a couple more. If I have a shear wave inside here, I have a shear critical. That's kind of interesting because now that means you can have shear wave on the inside that are going to die off, but you're going to hear shear reflections on that side. They're going to be abnormally large. And those abnormally large ones are the ones that are going to be confusing because they're going to look like Rayleigh waves. And they're going to be stronger than Rayleigh waves sometimes. So we have an S1 asymptote, and that S1 is an asymptote for all your shear. You have a P1 asymptote, that's for all your P1. You're going to have a critical angle asymptote, and what that's really going to mean is refractions have to stay on this side for the P, and your guided waves got to stay on this side. Or trap modes. So let's start varying the near surface thickness. We started with 850 feet. This is the model that we started with. And what we're going to do, I'll go forward and then come back. So the first thing, we're going to look at this inside cone right in here. That's 850 feet. That's reduced that to 450 feet. Now at 450 feet, lo and behold, look what happened. This is going to move up, and you got the first SS. Notice how that SS is moving up here, and you don't see anything until that S1 critical angle. So it's dead on this side. But everything is becoming asymptotic to the S1 asymptote. As I moved up again, oh, this one right over here, the P1, yeah, everything is between P1 and precritical. These are all your reflections that go into the guided wave sitting in here. Now, as I go up, you look at this, it starts getting more. It gets more coming in here. They're all becoming very close to that. Now, as we continue to go in that area, all of a sudden, you got energy that doesn't look like reflections, but now is beginning to look like Rayleigh waves coming in here. So your shear guided waves, they appear as ground rule. They are slower than that Rayleigh wave. Up here is where your guided waves, and they're showing your phase velocity. They're between precritical and the P1. So those two zones can be identified. We have some refractions coming out here. But notice that they're all asymptote to P1. These are just your large reflections coming over, starting to interfere with one another. As we continue to get to 150 feet, up to 90 feet, all of a sudden we see, what about this zone? It's kind of empty right here. Well, we're about 90 feet. Pretty soon, long wavelengths in your ground rope or Rayleigh wave are going to appear in this zone right in here. This zone right in here is S1, S1 type of reflections. Over here, all of a sudden, we notice that at 90 feet, if we go back again, whoops, if we go back, we see here, you can see the individual refractions, and this is guided wave. But when you go to 90 feet, guess what? You don't have guided waves. Now you have multiple refractions sitting in here that you were thinking were guiding waves. They don't exist. We go a little thinner than this, to 50 feet, you begin to notice that the waves are moving away from the precritical. And finally, as P1 thins, the refractions start to move to P2. Your post-SS1 and Rayleigh merge into this whole zone now. Now, you don't just go from the Rayleigh wave on to the next Rayleigh, you start from the shear critical. However, as you also notice, is your effectiveness of P1 and P critical, it's losing it. Everything's moving away because as you thin this upper zone, these two asymptotes don't become useful anymore. So finally, we're going to see what does this all mean. Here we have the refractions, and it goes from the P critical out to the P2. We're going to vary the refraction thickness. So as we vary the refraction thickness, we'll start with down here an infinite refractor. We're going to vary that thickness. Notice that these head waves go all the way out. They just keep on going over and over again, the amplitude. And they're starting right here at the P critical. You can't see it now. Notice when I go from half space to 200 feet, this amplitude disappears. Because what happens is, you convert it as a refraction, you're traveling out, but you're only 200 feet thick. Since you're 200 feet thick, you can't sustain a wave traveling outwards. It goes ahead and it loses amplitude. Then, when you have a multiple reflection up here though, that does not lose any amplitude because you're past critical angle, but then you convert and you're now going out as a refraction and you die out. So it's just a bunch of multiple refractions losing your amplitude, and when I get down to 100 feet, you can see how that amplitude disappears out here again. And then finally, down to 50 feet, and we look at it, we notice these right in here, these layers P2 thins, your refractions lose the amplitude. Your post-critical reflections are starting to decrease now because your layer here begins to thin. So finally, when we go ahead and we look at the field data, that we were looking at, we noticed that the refractions, or the shingling, are actually refractions. Now, what difference does that make? Well, if you're trying to use refractions in order to do any type of modeling, and you go into this sequence, it tells you, oh my gosh, I can use these too. All I got to do is account for the amount of delay that I should see due to these multiple bounces. And your refraction analysis can be extended. You just don't have this nice short ones right in here. So the velocity, what we had here, we showed velocity amplitude asymptotes. They actually quantify the events, where the events should go and how they move in the thickness. So we had a guided S waves where they occurred, we had radial waves where they could occur, P waves where they occurred, and we had refraction arrivals. And of course the objective was to find out what caused the shingling, and we see that it really is the thickness of two layers, the upper and the lower. I didn't really go through, I had to take it out because of time, but the P wave and the S wave velocity, especially the S, is really quite significant in how much amplitude you have. And finally, the lesson I was trying to show is that I tried to show that I was very systematic in adding more difficulty to the modeling. So I start with the simplest model and learn at each step what I'm actually introducing. So that's it. Thanks for your attention.